Hi again, welcome to the next video in the functions series. In this video we review the technique of integrating exponential functions. Integrating is the reverse of differentiation. As that was an easy strategy for exponential functions, so too is integration. Only a couple of small details to keep alert to. In the video on differentiating exponential functions, we established the relationship that if y was equal to e to the x, then the derivative dy dx was also equal to e to the x. It is easy, therefore, to work backwards to obtain the integral result. For example, if dy dx was equal to e to the x, then y is equal to e to the x plus the location constant. Or we can write the integral of e to the x dx is equal to e to the x plus c. So let's apply the result of the relationship to a specific example. So we have integral of e to the 5x dx. Well, the first thing we do is to write down the e to the 5x term. We then divide the e to the 5x by the derivative of the index, which is 5, because the derivative of 5x is 5. And then we add our location constant. So our result is e to the 5x over 5 plus c. Always talk to yourself when you are integrating exponentials. So say the e term remains the e term, and that is divided by the derivative of the index. Example 2. We have the integral of 2e to the 3x dx. Well, the 2 is a decoration, just write it down. So 2, e to the 3x, the term remains the same, so it's e to the 3x, divided by the derivative of the index, so the derivative of 3x is 3, plus the location constant. So the final answer is 2 over 3 e to the 3x plus c. The third example is the integral of 6e to the 4x minus 1 with respect to x. The 6 is a decoration, it's a constant, so write that down. The e term goes to the e term, so write down e to the 4x minus 1. Then we divide by the derivative of the index, which is 4. And then we add our location constant. So the final answer is 3 over 2 e to the 4x minus 1 plus c. Note that in all of these examples, the x in the index itself has an index of 1. We cannot integrate an exponential function which has the index of x greater than 1, for example, x squared or x cubed. We have to, in that situation, do some sort of transformation, but those transformations are restricted to higher level math courses. So the shortcut is you will not be asked to do something like find the integral of e to the x squared minus 1 dx. All the same strategies apply as we used with basic integration. For example, if we have negative indices, we might have the integral of 2 over e to the 4x with respect to x. So the 2 is decoration, so put it out the front of the integral sign and bring the e to the 4x up into the numerator. So we have e to the minus 4x dx. Integrate that, the 2 is, we write it down, e to the minus 4x goes to e to the minus 4x, divided by the derivative, which is minus 4. So tidying up, we have minus 1 over 2e to the 4x plus the location constant. If we're dealing with fractions which have one term in the denominator, for example, the integral of e to the 3x plus e to the x minus 4 all over e to the 2x with respect to x, we can divide through term by term, and so we then have e to the 3x over e to the 2x, which is e to the x, plus e to the x over e to the 2x, which is e to the minus x, and then minus 4 e to the minus 2x. Integrate each of those terms separately. We have e to the x minus e to the minus x, because we're dividing by minus 1, plus 4e to the minus 2x divided by the derivative, which is minus 2, and consequently that changed the minus to a plus. Tidy up, e to the x minus 1 over e to the x plus 2 over e to the 2x plus the location constant. Definite integrals are evaluated in the same way as for ordinary integrals. So the integral from 2 to 4 of e to the 2x minus 3 with respect to x gives us e to the 2x over 2 minus 3x, and the limits are 4 and 2. Substituting in, we have e to the 2 times 4, which is e to the 8 over 2 minus 3 times 4 is 12, minus, now we go to our second number, e to the 2 times 2 is 4 over 2 minus 6. Tidy up that, we've got an e to the 4 in both of those sort of odd terms, so therefore e to the 4 outside of e to the 4 minus 1, they've both got a common denominator of 2, and then we have minus 12 plus 6, which is minus 6. One caution with definite integrals involving exponentials should be given. Probably over half of the questions involve substituting the values x equals 0 and x equals 1. And these sorts of questions trick students all the time. So you must always remember that e to the 0 is 1, and of course e to the 1 is e. So, for example, we might have to evaluate the integral from 0 to 1 of 3e to the 4x dx. Well, the 3 is a constant, we leave it there. E to the 4x, we write that down, divided by the derivative, which is 4, from 0 to 1. And then we substitute. We have 3e to the 4 over 4 minus 3 over 4 e to the 0, which is not 0, which is 1. So therefore, tidying that up, we have a common factor of 3 and 4, so we take them out, and we're left with e to the 4 minus 1. Always be sensitive to the question with x equals 0, because e to the 0 is 1, and your examiners will always test you out on that point. Common questions involving the integration of exponentials incorporate the reverse chain rule approaches or the differentiate hence find approaches. The basic approaches are always the same as previously, so go to the website and look through the index under R or D for references to both the reverse and the differentiate techniques, or go to the relevant videos in the calculus section. For the reverse chain rule, we might have the integral of 3e to the 2x, bracket, 3 to the 2x plus 1, all to the 4th dx. So we allow u, or whatever variable we want to call it, represent the kind of bigger factor, which is e to the 2x plus 1. So we differentiate that, and we have du is equal to 2e to the 2x, and of course the 1 disappears. And so du is over 2 is equal to e to the 2x dx. We can now substitute into our original integral, because e to the 2x dx, as shown in red, is a half du. So our integral becomes 3 over 2, because the 3 was in there as a decoration, 3 over 2, the integral of u to the 4th du, which integrates to 3 over 2 u to the 5th over 5, which, tidy up, we have 3 over 10, replace the u with what we defined it to be, e to the 2x plus 1 to the 5th, plus the location constant. If we were doing a differentiate hence find question, we might have the first part being differentiate 2x e to the x. Well, clearly we have two functions of x multiplied together, so it's a product rule. And if you use the normal product rule relationships and approaches, then the derivative becomes 2 times e to the x plus 2x e to the x. So the second part would be the integral of x e to the x dx. So in normal practice with the differentiate hence find questions, we write down what we have done. So it's the derivative with respect to x of 2x e to the x, and that gives us 2 e to the x plus 2x e to the x. So we add our integral signs and our dx terms, and we have the integral of d dx of 2x e to the x dx equals 2 integral of e to the x dx plus 2 integral x e to the x dx. Cancel the 2's. The integral of the derivative is just the thing itself. So on the left-hand side we have x e to the x. On the right-hand side, the 2's gone, so the integral of e to the x is simply e to the x. And then we have the integral of x e to the x dx, which is our question. So we leave that on the left-hand side, and we take the e to the x across the other side. So our answer is the integral of x e to the x dx is equal to x e to the x minus e to the x plus the location constant. So all good. But remember, when you are integrating exponentials, the e term remains the e term, and then we divide by the derivative of the index. So that is the story of integrating exponentials. It is a relatively straightforward process, but keep your focus on what you are doing at each step. Of course, you keep your attention by talking to yourself while you work through the problem. Thanks for watching this video. Go and do some exponential integration questions in Test Yourself 1 on my website at drjaysmaths.com. Good luck. See you in another functions or calculus video.